Now, we could derive a variety of other identities and formulae, but these will more than suffice for our purposes. Before we conclude, I should give you a word on how we can prove identities like this. And at the heart of what we're trying to do is we're trying to show that two sets are equal. And you scratch your head and says, this is ridiculous. If you give me an object and another object, can't I tell by just looking at it that they are the same? Of course I can, if the objects are finite. But it gets harder if the objects are infinite in terms of the number of elements in it. It gets harder if the objects are represented in apparently very different looking ways. And so it will be useful to have in hand a procedure which tells us how we can go ahead and show that two sets, two objects, are in fact the same object. So let's start with a subset A and a potentially different subset B of some universal set. Now, what does it mean to say that A is equal to B? Well, the finite domain, it's easy, right? If you have 10 objects in A and 10 objects in B, I can just look at them and say, well, these are the same objects. It's obvious. But how do you do it if A and B are infinite? I can't just eyeball them, can I? I need a more formal procedure. Okay. So what does it mean to say they're equal? Well, if they're the same, then there's a two-part answer to this. Reach into the set on your left. Call it A. Pick out a jelly bean, an object, an element, a marble, okay, a number. This is something in A. If A and B are really the same, then any object here must have a counterpart here, which is exactly the same. So the first part would be to say that one needs to demonstrate that every element in A is also in B. It sounds very abstract, right? But we'll run through a concrete setting in a moment. If I can show this, what have I actually done? I've shown that A, in fact, is a subset of B. So this is the first part of a demonstration. Show that every element in A is also in B. A is a subset of B. All right, now I know that A is contained in B. To show the obvious, we'll settle it. Repeat the story by saying, well, here's an element from B. Pull it out, kicking and squealing, and say, well, is it there in A as well? Right? If this frog in this collection of frogs is in A, and it's true for every frog in the collection of frogs which is B, then the collection of frogs which is B must be contained in the collection of frogs which is A. B is a subset of A. If I can show that both A is a subset of B and B is a subset of A, then I've got no room to wiggle. I've got no place to turn. It must be the case that A and B are identical. Okay. In abstract settings, in infinite settings, this is always the way we proceed. We break down equality by first showing that everything on one side is contained in the other, and then showing that everything on the other side is contained in the first, and together we achieve equality. Now, this is very, very abstract. Right? If you haven't seen arguments like this before, it looks weird and say, oh, gee, I didn't get it. Oh, but of course, that's because our intuition is founded upon finite elements, finite groups, where inspection can immediately tell us an obvious answer. But it gets much harder in abstraction. It gets much harder when you have infinite collections. We can't just eyeball things. That's why one needs a formal procedure like this. Now, here is a formal procedure for checking equality of sets. We can put this to work immediately in checking the validity of any of the identities or the formulae that I've shown you. Right. Let's immediately put this to case, and let's take as a test case the distributive property of unions over intersections. We claim that the union of A with B intersection C is the same as the intersection of A union B with A union C. Now, how would one show this? Well, let's first start by showing that every element, omega on the left-hand side, is also in the right-hand side. If that is the case, then the set, which is this complicated-looking thing on the left-hand side, must be a subset of the set which is on the right. So let's begin by picking a test element. Suppose omega is an element of the set on the left. Omega is an element of A union B intersection B, C. We now need to show that this is also an element of the set on the right. Okay, well, what does it mean to say that omega is in the union of A with B intersection C? Well, what does union mean? Union is a sort of inclusion, right? It sort of bloats things out. It makes things bigger. It means that that omega must be in A, or it must be in B intersection C, or possibly, of course, in both. Remember, unions are not exclusive. All right, now we have two possibilities. In settings like this, I'm very fond of an adage of the great Hungarian mathematician and educator George Polya. He used to say, when you have two things to say first the first thing and then the second thing. And you look at me and say, duh. Right. Of course it sounds trite and ridiculous, but I can't tell you what an important and basic principle this is. Graduate students dealing with complicated settings in science or engineering are trying to keep something in mind where there are 30 different varieties of things going on. They're trying to keep everything in mind simultaneously, and they go crazy. They've forgotten Polya's very wise adage. When you have many things to do them one at a time. When you have two things to say the first thing first, then say the second thing. All right. In our setting, omega is in A or omega is in B intersection C. Let's not worry about both of them simultaneously. Let's take them one at a time. Suppose omega is in A, and let's see where this train of thought goes. If omega is in A, since union is an increasing operation, then omega is certainly in A union B, and omega is also in A union C. If omega is in both A union B and A union C, then clearly it's there in the intersection of the two, and therefore omega is in the intersection of A union B and A intersection A union C. Good, we have established that in the case omega is in A, and omega on the left-hand side is also on the right-hand side. What if omega is in B intersection C? Okay, here's a second possibility. Well, if omega is in B intersection C, then omega must be, by the definition of intersection, both in B and in C. Since omega is in B, it is there in A union B. Since omega is in C, it is there in A union C, and therefore it is manifestly there in the intersection of A union B and A intersection C. In both cases, an omega on the left is on the right, and therefore the set on the left is a subset of the set on the right. We've concluded the first part in the verification of equality. We now need to reverse the direction. And, of course, the proof is exactly the same. It follows exactly the same pattern. And as a sanity check, I will let you work through the steps. Mirror what you did on the left, do it on the right. And verify now that every omega which is on the right must also be on the left. In other words, the set on the right is a subset of the set on the left. And with both parts established, we have nowhere to turn. The two sets must, in fact, be exactly the same. Notice already here, in a setting like this, ordinary intuition was not going to suffice. We actually needed a formal methodology, a way of proceeding to show that these two objects were the same. And here's a need which is manifest for a formal procedure. Of course, you can use this to verify the other distributive property, that intersections distribute over unions. Do so. It will be a valuable test case of your understanding. And to burnish your burgeoning understanding of a method of proof, try the following. Now go back and try to verify De Morgan's laws using this concrete procedure. When you're ready, come back and we will summarize what we've done.